Okay, so section 2.2, generally people like more than 2.1. So I think you're going to find the stuff that we do today easier. You're going to want to make sure you have your graphic calculator good to go. But here's where we start. Uh, I'm going to give you guys later on the formal definition of a limit, okay? Because, well, that's something you're going to have to learn. We'll get to that later. But so right now is informal, meaning it, how do you want to say it? It's less exact. It's not mathematically absolutely correct, but it's good enough for us to understand. Now, here's what I want to pick up off of, okay? Here's why we're moving from the tangent problem, which we just did in section 2.1, to limits, okay? Again, I'll ask the same question I asked Larry before. What is the width? Right now I have a width within an interval, okay? We're looking from 1 second to 2 seconds. So what's that width? 1. Then I'm looking from 1 second to 1.5 seconds. What's that width? And then I'm looking from 1 second to 1.1 seconds. What's that width? 0.1. So what is our width approaching? And what we say, how we approach 0, because we definitely want to do that. We want the width of that interval to be 0 at some point. We call that the limit. We want it to approach something, and we find a result. So in order for this guy, Archimedes, way back, to formulate some calculus ideas, he wasn't able to formally write them down in a way that we could really understand. Now, this was probably in his brain, but it wasn't until really the 1500s that we got this idea of a limit. Calculus is not possible without the idea of a limit. And finding the exact slope of a tangent line at one point is not possible without the concept and idea of a limit. So that's what we have to work through. So we're going to step away from the tangent problem. We're going to put it over here for a while, and we're going to pick it back up in a little bit. But we're going to see and discover this idea about limits. And here's the notation, and you'll get used to this a lot. I know it looks funny, but it says, this literally says the limit as x approaches. You see that arrow right there? So x approaches a of the function equals L. What that means, we'll write it down. The output, or y value, of the function approaches some value, we'll call it L, as x approaches some number, we'll call it A. We're going to go bare bones here. You ready? Okay, take out your calculator. You don't have to write this down. I'm just going to do one basic example. So the limit as x approaches a, my a value is 2. We're going to have x approach 2 of the function 2x minus 3. So what that means is, what are the output values approaching, the y values approaching, as x gets really close to 2? Well, we'll look at our calculator and we'll look at it by hand. What does that graph look like, you guys? It's a line. It goes through -3. Okay, so I'm going to plot -3. I go up 2 and over 1, up 2 and over 1. So, you can look at this. As we look at the graph, okay, can somebody guess, as my x values get really close to the value 2, can you guys tell what the output or the y values are getting really close to? Yeah. As I get really close to these x values of 2, you can see that the y value is getting really close to 1. You can just plug it in. Plug it in. 2 times 2 is 4, minus 3 is 1. But there's so many limits that we can't just plug in. So we need to look at data. Can you see graphically how that's happening? Let's look at the data perspective of it. Let's type into our calculators 2x minus 3. And what I'm going to do then is I'm going to go to my table. And what value did we want to approach again? We want to approach 2. So let's plug in 1. And then let's plug in 1.1, 1.2, 1.3, 1.4, 1.5, 1.6. So it goes to negative 1, negative 0.8, negative 0.6, negative 0.4, negative 0.2, 0.2. Am I close enough yet to see what that limit is? No, so let's get really close. Let's choose a value like 1.9. What would be a good next value to choose to get really close? 1.99, very good. And what would be another good value to choose? 1.999 and 1.9999. Now, what does it look like that value is approaching? 1. So whether you look at the output graphically or by data, is it clear to you that it's approaching 1? Yes, in fact, it is. So we could say that the limit of this function is equal to 2. I'm sorry, 1. Wow, just totally messed it there. All right. So, but I want to be clear. Elizabeth said, can't we just plug it in? Yes. In this scenario, you may simply just plug it in. We have to look at the differences between functions where you can do that and functions where you can't do that. So let's go back here, okay? 1/2 x squared minus x plus 3. Let's plug that into our calculator, okay? 0.5 x squared minus x plus 3. And I'm going to view that in a normal viewing window, a standard viewing window. So I'm going to go zoom 6 for zoom standard. And it says, what is x approaching? 2. So here's what I want you to do now. Press trace. If I want x to approach 2, which button should I press? Move it to the right. So are my x values getting closer? Yeah, you can look. X is 1, y is 2.5. And as I get closer, x is 1.9, y is 2.9. What does it look like it's getting pretty close to, possibly? Looks like it could be 3. Let's go to the other side of it. 2.5, now I'm going to approach it from the other side. Looks like it's over 3. It's still slightly over 3. 2.1, 3.1, still slightly over 3. Yeah, I mean, it looks like it's going to be about 3, right? If I wanted to get a better estimate, what could I do? Go to your table, and we can punch in values like 1.9, 1.99, 1.999. Does that look convincing that it's headed towards 3? Yes. And in fact, in this scenario, we can draw it, and yes, beyond a shadow of a doubt, okay, as x approaches 2, the limit approaches 3. That is what happens, okay? The answer to this question is 3. The limit is equal to 3. And as Elizabeth said before, we could simply plug in that value. 1/2 times 2 squared minus 2 plus 3. And you would end up with a result of 3. You can just substitute it in this scenario. Okay, that's bare bones. Is there any question or confusion about limits before we try to get to some examples that are more interesting? The limit is the y value that the function approaches as the x values approach something else. You ask a good question. Every year, somebody does have again the question, what is a limit? It's what the y values are approaching. Um, that's a very, very good idea. What that ends up doing for us later on is your idea ends up solidifying that it will be continuous, but not necessarily that it's a function. You could be discontinuous but still be a function. So I'm going to get to your question in about a week. Okay? All right. How about square root of x plus 4? What does that look like? It's like a half parabola. It's shifted which direction? To the left 4 units, and it looks like that. So you're always better off if you can view the function in your brain, okay? And if you can see that, great, you're in good shape. Does this function have a value at x equals 0? Yeah, in fact, at x equals 0, right here, 0, as x approaches it from either side, we have the limit. So to answer Zach's question earlier, what's the limit? It's the y value, the output that it's approaching. What value do you think it's approaching? What do you think is the y value going to be? 2. And that was easy enough because you could plug in 0 and you would get 2. Awesome. Question? No? Okay, so then this one right here, look at this one. X squared minus 3x over x minus 3. Does anybody have an idea what that looks like? Good idea, but no, it's actually going to look like a line. And I'll show you why. This is really cool. Can you plug in 3 into that function and get a result? No, this is discontinuous at x equals 3. X cannot be equal 3. So as you look at it, it says x is approaching 3. So what do we do in a scenario like this? Great, we could look at it on our calculator. And since that was suggested, that's what I'm going to look at first. Let's go to our calculator, and I'll show you the algebraic way to work through this. So this is one of those exceptions like, oh no, what do we do now? Well, never be afraid if you're trying to evaluate a limit, never be afraid to go to your calculator and use your table. We have parentheses, x squared minus 3x divided by x minus 3. No. It could be back in that shelf. No, I did not take it. She's always blaming me. All right, so we have that. And so what I'm going to do is I'm going to, again, view it, zoom 6 in this window. So what shape does that look like? Does it look like it's discontinuous at x equals 3? No, in fact, it looks like you could plug it in and get a value. And I'll show you why. I'll show you why. Your calculator misleads you. Let's go to our table so we can get a better idea of what's going on here. What value should I plug in instead of 1.9? Let's plug in 2.9. Let's plug in 2.99. Let's plug in 2.999. What does it look like it's approaching? 3. But if I actually plug in the value of 3, what does it say? Error because it's discontinuous. Yes, that's exactly what's going to happen here. We can rewrite it. H of x is equal to x times x minus 3 over x minus 3. So you end up with this function, h of x is equal to x. Now, this is so important that you guys catch this. It wants to look like the function wants to look like this. It wants to look like h of x is equal to x, but it doesn't. It doesn't. It has a hole in it. It's discontinuous, meaning it's not evaluated at the spot 3. if you plug in 3, you end up with troubles. So what does h of x equal x look like? Yeah, it's just a line that passes through 0 with a slope of 1. So I'll draw it. But that's not really fair to draw it like that, is it? Because you can't plug in 3, can you? So at the x value of 3, does anybody know what the y value would correspond at that point? It would also be 3. I'm going to draw a hole right there. It doesn't show up on your calculator because the way the pixels work, but there is a hole in the function right there. Question? You would have to get the calculator to want an exact value of 3 at that one spot, which you could do if you did this. Zoom as a decimal, number 4. Oh, do you see it? Everybody watch mine. We got the calculator to do it. Look, here's 1. Here's 2. Look what happened at 3 right there. We got it to do it. It was amazing, right? Well, then there's a good chance that it won't choose the value 3 then at that spot. That it would choose like 3.1426 or I mean it doesn't like to choose that exact spot unless you force it to. So okay, so there we have it. Yeah, if you traced it, it would actually give you. Yeah, let's do it. It's so fun. All right. This is why I wore my outfit today. All right. So we can go trace and we can follow it. As you can see, it's choosing those values. And as we get to the value of 3, what's going to happen? Oh! The calculator broke. And one more, it gets it. Isn't that cool? So, awesome. Do you remember what this one looks like? Do you remember what happened when we looked at that the other day? That was the barcode function. So I'm going to write here, zoomed in. Yeah, if you... Okay. If you don't believe me, you can do it. We did it the other day, right? When you zoom in on sine of 1 over x, you get the barcode function. All right, then we'll do it together. Y equals sine of 1 divided by x. And as we'll zoom as a normal viewing window, and you can see here, it doesn't look all that interesting, does it? But then you might not be in radians, you might be in degrees. So then if I zoom in right on that spot, you start to see a little barcode activity. Zoom in again. Oh no, I just zoomed normal, sorry. You guys got the idea though, right? That's what happens. What's that? It might not. Now, shh, watch this, guys. Shh. What's my x value approaching? My x value is approaching 0. Shh. Watch what happens. If we plug in 0, you have an error. Why? Because you would have 1 over 0 for your function, and that does not work. Okay? So let's try this. What's a number very close to 0 we could plug in? 0.1. Let's try 0.01. Let's try 0.001. 0.00001. 0.00001. As you guys look at this, does it look like these values are approaching anything real specific? No. In fact, it continues to bounce up and down. And therefore, if it's not decisively approaching a specific value, limit does not exist. In honor of you guys, I watched Mean Girls for the first time ever on Friday night. Kevin G. Yep, I saw Kevin G. I've got to try to contact Katie so we can see her rap. I agree, it's amazing. I want to see it too. But so it's possible that you would have a limit that simply just does not exist. And so, if you flip it over, so in order to define whether or not a limit exists, we need to look at both sides of it. We need to approach it from the left. We also need to approach it from the right. And so the only difference in the notation is, do you see the negative sign above the A? That means that you approached it from the left-hand side. Now, if you see a positive sign above the A, that means that you're approaching it from the right-hand side. So if you're approaching from the left, you're approaching from smaller values. And if you're approaching from the right, you're approaching from greater values. So we're not going to get through all this, but this is such an important example for you to understand the concept of limits, okay? So it says, let f of x be the graph to the right. So all this red stuff here is the graph of f of x. And it says, use the graph to evaluate the following limits. So this says I'm going to approach x. X is going to approach, -4. And is it going to approach -4 from the left or from the right? From the left. So if I approach it from the left, what's the output approaching? What's the output approaching right at that spot? 3. Meaning, as the x values get very close to -4, the output, you guys told me, is going to be approximately 3. That means you're approaching it from the left. Now, let's look at the other one. Limit is x approaches -4, and then there's a positive sign. That means I'm approaching from the right. What would the output be there? -2. Is the function actually evaluated there? No, it makes a jump up to the other spot. And so that was my point to Emma's question earlier, is that we're going to investigate those jumps and when they happen, when they don't, and how limits tie that together. What if we approach -1 from the left? Yeah, 4. What if you approach it from the right? It's also 4. Notice that it's the same in those scenarios, isn't it? Okay, that's going to be very important as we move forward. Can you actually plug in -1 and get a value? Yeah, you can. You get a value 4. It's defined right there. How about as you approach... so that raises... we're going to skip that one. I don't know why I put that in. How about as you approach 2 from the negative? As you approach 2 from the negative, from the left, you have a value of -1. What have you approached 2 from the right? How's it 5? If it says the limit as x approaches 2, here's what that means. That the left and the right have to be the same. Is the left and the right the same? No. So the limit does not exist. How about the limit as x approaches -1? Are the left and the right the same there? So the limit exists. It would be 4. So we're going to pick up with that idea tomorrow, and you guys will have a decent amount of time in class to work on assignments.